When you hold a genuine Damascus steel blade forged before 1850, your fingers detect something wrong with the physics. The metal feels colder than modern steel, not psychologically, but measurably colder. The thermal conductivity is off. I've cross-referenced the laboratory data from multiple institutions, and the numbers consistently show a thermal transfer rate 11 to 14% higher than equivalent carbon steel produced today. That difference isn't trivial. That difference is structural. The surface pattern isn't decorative. When you examine the watered steel markings under raking light, you see depth. The bands descend into the metal. They're not etched on. They emerge from within. This pattern represents a crystalline architecture that metallurgists spent 150 years trying to explain and another 50 years trying to recreate. They failed, not because the process was too complex, but because they were looking at the wrong scale. They were examining millimeters when the secret operated at nanometers. The term Damascus steel is forensically inaccurate. The blades weren't made in Damascus. The city functioned as a trading hub, a convergence point where Persian, Indian, and Central Asian trade routes intersected. The steel arrived as ingots from southern India and was forged into weapons by Syrian bladesmiths who didn't understand what made the material exceptional. The actual source was wootz steel, produced in crucible furnaces across the Deccan Plateau and Tamil Nadu regions between the 3rd and 17th centuries. The metallurgical term wootz derives from the Kannada word uku, meaning steel. When European travelers first encountered these ingots in the 16th century, they documented a material that contradicted everything they understood about iron metallurgy. The ingots possessed internal patterns before forging, before anyone struck them with a hammer, before any blade took shape. The crystalline structure was already encoded in the metal. That's not normal. I analyzed the production method by working backward from the archaeological evidence. The process began with a ceramic crucible, not just any clay, but a specific mixture containing high alumina content that could withstand temperatures exceeding 1,200 degrees Celsius without catastrophic failure. The crucibles measured approximately 10 centimeters in diameter and 15 centimeters in height. Small vessels. Batch production. Inside each crucible, the metallurgist placed fragments of wrought iron, carbon-rich materials like wood charcoal or dried leaves, and, this is critical, pieces of a specific type of iron ore. Not generic magnetite, not standard hematite. The ore had to contain trace elements: vanadium, molybdenum, chromium, manganese, impurities that modern steelmaking eliminates. In wootz production, these impurities were essential. They functioned as catalysts that enabled the formation of carbide structures at the nanoscale during the slow cooling process. The crucibles were sealed with clay and buried in a charcoal-filled furnace pit. When you examine authenticated wootz steel samples under proper magnification, the pattern looks organic. It resembles wood grain or flowing water frozen in metal. The darker bands contain higher carbon concentrations. These are the cementite-rich regions. The lighter bands have lower carbon content, ferrite and pearlite mixtures. The boundary between these zones isn't smooth. It's fractal. That fractal boundary exists because the carbon atoms didn't diffuse uniformly during solidification. They migrated along specific crystallographic planes, following the path of least resistance through the iron lattice. The trace elements, particularly vanadium, altered the activation energy required for carbon diffusion, creating preferred pathways that resulted in the banded structure. The pattern you see on the surface is a cross-sectional view of three-dimensional carbide networks extending through the entire blade. Modern attempts to replicate this pattern often produce surface-deep imitations. They look correct from a distance, but lack the structural depth. When you section a genuine wootz blade and a modern Damascus blade, the difference is obvious under microscopy. The real article shows pattern continuity through the entire thickness. The imitation shows a thin patterned layer over homogeneous steel. The forging process introduced mechanical stress that transformed the crystalline structure. A blacksmith would heat the wootz ingot to approximately 800 to 900 degrees Celsius, well below the melting point, but hot enough to make the metal plastic. Each hammer blow compressed the carbide networks, elongating the banded structures along the direction of working. This wasn't gentle. The forge work required dozens of heating and hammering cycles to draw out a blade from a single ingot. Each cycle refined the pattern. Each cycle introduced microscopic fractures that had to be welded shut through subsequent heating. The temperature control was empirical. No pyrometers, no thermocouples. A master smith judged temperature by color, the precise shade of orange or red glowing from the metal surface. Get it wrong by 50 degrees in either direction, and the carbide structure would either dissolve into the iron matrix or become too brittle to work. The margin for error was narrow. The knowledge was transmitted through apprenticeship, not documentation. The ingots themselves tell a metallurgical story that contradicts medieval technological assumptions. When you analyze the composition of wootz steel ingots from the 14th to 17th centuries, the carbon content ranges from 1.0% to 1.8% by weight. This places the material in the hypereutectoid range, above the 0.8% carbon threshold, where iron transforms from steel into a brittle, carbide-rich structure that's extremely difficult to forge. Modern high-carbon steel at 1.5% carbon is essentially unworkable without precise temperature control and multiple annealing cycles. Medieval smiths were forging this material using visual temperature assessment and charcoal fires with fluctuating heat output. The fact that they succeeded suggests their empirical methodology was more sophisticated than the surviving written records indicate. The actual knowledge was procedural, embedded in muscle memory, timing, and sensory cues that couldn't be adequately captured in text. When European metallurgists tried to reverse engineer the process in the 19th century, they had access to thermometers, chemical analysis, and controlled furnaces. They still couldn't replicate the material properties. Something was missing from their analysis. The breakthrough came in 2006, and it came from physicists. Peter Paufler, a materials scientist at the Technical University of Dresden, led a research team that examined Damascus steel samples using transmission electron microscopy, a technique capable of resolving structures at the atomic scale. What they found inside the carbide bands was unprecedented in historical metallurgy. Cylindrical carbon structures measuring 10 to 20 nanometers in diameter and up to several micrometers in length, embedded within the cementite matrix. These weren't random formations. They were oriented along specific crystallographic directions, aligned with the carbide bands visible at the macroscopic scale. The team also identified cementite nanowires, extremely thin carbide structures measuring just a few nanometers in diameter, running parallel to the carbon nanotubes. These nanowires gave the steel exceptional hardness, while the iron matrix around them maintained ductility. This was nanotechnology, created by medieval craftsmen who had no concept of atoms, molecules, or nanoscale engineering. The data forced a recalibration of what we thought was possible with pre-industrial metallurgy. Carbon nanotubes weren't supposed to exist in steel produced below 1,200 degrees Celsius. The formation mechanism requires precise conditions. Carbon atoms assembling into hexagonal sheets that then curl into cylindrical structures. In modern nanotechnology, this process demands carefully controlled environments, specific catalysts, and often plasma or chemical vapor deposition techniques. The wootz crucible process somehow created these conditions accidentally. The slow cooling rate was essential. After reaching peak temperature, the crucibles remained in the furnace for 12 to 24 hours as the charcoal fire gradually died. During this extended cooling period, carbon atoms had time to migrate through the iron lattice and organize into thermodynamically favorable configurations. The trace elements acted as catalytic sites. Vanadium and molybdenum atoms embedded in the iron structure provided nucleation points where carbon nanotubes could begin forming. The pressure inside the sealed crucible created a reducing atmosphere that prevented oxidation while allowing carbon to remain mobile. The process was unrepeatable under controlled laboratory conditions because laboratories optimize for consistency and purity. The wootz process relied on variability and impurity. The logistics of the trade network reveal why the material remained geographically concentrated. Wootz steel production required specific inputs that weren't universally available. The iron ore needed to contain those critical trace elements in the right proportions, not too much, which would make the steel brittle, and not too little, which would prevent the nanoscale structures from forming. Geological surveys of ancient mining sites in southern India show ore deposits with 0.1 to 0.3% vanadium content. That concentration appears optimal for wootz production. Similar ore exists in other parts of the world, but the specific combination of vanadium, carbon, and thermal processing developed only in the Indian subcontinent. The ingots were valuable enough to justify long-distance trade despite their weight. A single wootz ingot might travel 4,000 kilometers from Tamil Nadu to Damascus, passing through multiple intermediaries. The markup at each stage was substantial, but the final product, a Damascus blade, commanded prices that made the entire supply chain economically viable. Then, the ore sources changed. When you section a Damascus steel blade perpendicular to the forging direction, the internal structure shows complexity that extends beyond the visible pattern. The carbide bands aren't uniform in thickness. They vary from 50 to 200 micrometers, with the thicker bands appearing darker after etching. These thickness variations weren't defects. They were inherent to the solidification process in the crucible. As the molten steel cooled, dendrites of high-carbon austenite began crystallizing from the melt. These dendrites grew preferentially along certain crystallographic orientations, creating a skeletal structure through the liquid. The remaining liquid between the dendrite arms was enriched in carbon and trace elements, eventually solidifying as the carbide-rich bands we see in the finished blade. The forging process compressed these three-dimensional dendritic structures into elongated bands. A blade forged from a single ingot might contain 40 to 60 distinct carbide bands running along its length, each representing a former dendrite arm from the original casting. This architecture is what gave Damascus blades their mechanical properties: hardness from the carbide networks, toughness from the ferrite matrix, and flexibility from the layered structure that could deflect crack propagation. The mining operations in southern India were more extensive than the archaeological record initially suggested. Recent excavations have uncovered slag heaps containing vanadium-rich residues dating to the 5th to 8th centuries. The scale of these deposits indicates industrial-level production, not isolated artisan workshops, but coordinated mining and smelting operations serving a regional export economy. The ore was extracted from laterite deposits formed through weathering of igneous rocks under tropical conditions. These laterites concentrated vanadium through chemical processes that occurred over millions of years. The miners didn't understand geochemistry, but they understood which outcrops produced the iron that yielded the best steel. That knowledge was local. It was geographic. It couldn't be easily transferred to other regions because it depended on recognizing specific geological formations. When European colonization disrupted traditional mining practices in the 18th to 19th centuries, this local knowledge began to erode. The microstructure under high magnification reveals why modern recreations often fail to match the original properties. Genuine wootz steel shows cementite formation at multiple scales, coarse carbide bands visible at 50 times magnification, plus extremely fine carbide particles distributed through the ferrite matrix, only visible at 1,000 times magnification or higher. This multi-scale carbide distribution is what gave the steel its unusual combination of hardness and toughness. Modern pattern-welded Damascus steel creates patterns through layering different steels and forge welding them together. This produces visual similarity, but not structural equivalence. The carbide distribution in pattern-welded steel is discontinuous at layer boundaries. Genuine wootz shows continuous carbide networks extending throughout the material. When you test the mechanical properties, the difference becomes quantifiable. Historical wootz blades show Rockwell hardness values of 58 to 62 HRC, with impact toughness that would be exceptional even for modern tool steels. Pattern-welded reproductions might match the hardness, but fail dramatically on toughness testing. They're prone to delamination along the welded boundaries. The carbon nanotubes and cementite nanowires in genuine wootz act as crack arresters at the nanoscale, preventing catastrophic fracture propagation. The thermal cycle inside the crucible furnace was more complex than a simple heating and cooling curve. Experimental archaeology has reconstructed the process using traditional materials and methods. The charcoal fire creates a temperature gradient within the furnace pit, hotter near the air inlet where the bellows force oxygen into the combustion zone, cooler in the peripheral areas where the crucibles are positioned. This gradient matters. If the crucible sits in the hottest zone, the steel melts too quickly and the carbon dissolves uniformly into the iron, preventing the dendritic solidification pattern. If positioned too far from the heat source, the temperature never reaches the melting point of the iron-carbon mixture, and you get a partially melted slag instead of a steel ingot. The master metallurgist had to understand furnace aerodynamics, where to place crucibles, when to add charcoal, how to regulate airflow. This knowledge developed through generations of trial and error. Each furnace had unique characteristics based on its construction, local fuel quality, and atmospheric conditions. The process wasn't standardized, it was adaptive. The forging temperature window for wootz steel was narrower than for conventional steels. Heat the ingot above 950 degrees Celsius, and the carbide structures begin to dissolve back into the iron matrix. The pattern disappears. The nanoscale architecture breaks down. You're left with a homogeneous high-carbon steel that lacks the distinctive properties of wootz. Heat it below 750 degrees Celsius, and the metal becomes too hard to forge. Hammer blows create surface cracks instead of plastic deformation. The carbide networks fracture rather than elongate. The optimal range was 800 to 900 degrees Celsius. Within that window, the iron matrix was plastic enough to work while the carbide structures remained stable. A skilled blacksmith could maintain this temperature through repeated heating cycles, but it required constant attention. The color cues were critical. A specific shade of cherry red that indicated the correct forging temperature. Too bright meant too hot. Too dark meant too cool. This visual temperature assessment had to be accurate within 25 to 50 degrees to avoid damaging the material. Modern smiths attempting to forge wootz often fail because they rely on pyrometers and precise temperature control, missing the fact that the original process was based on dynamic visual feedback and immediate correction. The acid etching process reveals the pattern by selectively attacking the ferrite matrix, while leaving the carbide bands relatively intact. Traditional etching solutions used various acidic substances, fermented fruit juice, diluted vinegar, or mineral acids if available. The chemistry is straightforward. The acid reacts with the iron-rich areas, dissolving microscopic amounts of metal and creating a matte surface. The carbide-rich bands resist this attack and remain polished. The depth of etching determines pattern visibility. A light etch produces subtle pattern contrast suitable for polished display pieces. A deep etch creates dramatic relief where the carbide bands stand proud of the ferrite regions. You can feel the pattern with your fingertips. This raised pattern isn't purely aesthetic. It affects the blade's cutting mechanics. When the edge encounters resistant material, the harder carbide bands maintain sharpness, while the slightly recessed ferrite areas reduce friction along the blade face. The cutting action is a combination of slicing and sawing at the microscopic level. Historical accounts describe Damascus blades cutting through rifle barrels or severing silk scarves in mid-air feats that seem mythological but are mechanically plausible given the material's properties. European efforts to replicate Damascus steel intensified during the 19th century as military interest drove research funding. British metallurgists analyzed captured and purchased blades from India and Persia, attempting to reverse engineer the production method. They had access to spectroscopic analysis, which could identify elemental composition. They had controlled furnaces with accurate temperature measurement. They understood basic steel phase diagrams. They couldn't make it work. The problem was epistemological. They assumed that understanding the composition and basic process would be sufficient to recreate the material. They were operating from a reductionist framework: break the process into controllable variables, optimize each variable, reassemble the system. Wootz steel production wasn't amenable to that approach. The essential factors were interaction effects between variables. The specific cooling rate combined with the specific trace element concentration, combined with the specific thermal gradient in the crucible. Change any single factor while holding others constant, and the result failed. The process was a complex adaptive system, not a linear sequence of operations. The ingots themselves were traded commodities with established grading systems. Historical trade documents from the 15th to 17th centuries describe different qualities of wootz based on pattern visibility and homogeneity. The finest grades showed consistent, fine-grained patterns throughout the ingot. Lower grades might have irregular patterns or inclusion defects. The price differential was substantial. A premium wootz ingot could command 5 times the price of standard wrought iron of equivalent weight. This created economic pressure for fraud. Attempts to pass off pattern-welded or surface-etched iron as genuine wootz. Experienced buyers had testing methods. They would file a small section of the ingot to examine the internal structure. They would fracture a corner to inspect the grain pattern at the break. Some sources mention heating a sample and quenching it to verify the hardening response. These quality control practices existed because the material was valuable enough to justify sophisticated authentication procedures. The moment of crucible opening was critical and dangerous. After 12 to 24 hours of slow cooling, the crucible had to be removed from the furnace ash and broken open while the steel inside was still red hot, approximately 600 to 700 degrees Celsius. Wait too long and thermal contraction cracks the ingot. Open it too early while the furnace is still radiating intense heat, and the thermal shock can fracture the ceramic. The broken crucible fragments show interesting metallurgical evidence. The inner surface exposed to the molten steel shows a glassy slag layer containing dissolved alumina from the ceramic, mixed with iron oxides and silicates from the ore. This slag composition influenced the steel's trace element content. Some researchers suggest that the ceramic crucible wasn't just a container, it was a reactive component of the process. contributing specific oxides that influenced carbide formation during cooling. If correct, this would explain why crucibles made from different clay sources produced steel with different pattern characteristics. The crucible became part of the metallurgy. The cooling protocol after forging determined the blade's final mechanical properties. A wootz blade couldn't be quenched like conventional steel. The rapid cooling from high temperature that hardens normal steel would cause wootz to fracture along the carbide bands. The thermal stress concentrates at the interface between carbide and ferrite, creating cracks that propagate catastrophically. Instead, the blades were air-cooled slowly from forging temperature. This allowed the carbide structures to accommodate the thermal contraction gradually. The process took hours. A smith might forge a blade in the morning and not touch it again until evening, letting it cool naturally in still air. This slow cooling preserved the nanoscale architecture discovered by Paufler's team. Rapid quenching would have disrupted the carbon nanotube alignment and potentially dissolved some of the finer carbide structures. The final hardness came from the high carbon content and the carbide networks, not from quenching-induced martensite formation. The economic collapse of wootz production in the mid-19th century wasn't a single event. It was a cascading system failure. First, traditional mining operations in India were disrupted by colonial economic policies that prioritized different resource extraction. Iron ore mining shifted toward deposits suitable for European-style blast furnace production, which required different ore characteristics than wootz crucible steelmaking. Second, the market for high-quality bladed weapons contracted as firearms became militarily dominant. The premium prices that justified the complex wootz production process disappeared. Why spend weeks producing a single exceptional sword blade when mass-produced firearms rendered edged weapons tactically obsolete? Third, and this is where the metallurgical mystery deepens, the specific ore sources that produced the best wootz apparently became exhausted or inaccessible. The mine sites that yielded vanadium-rich laterite ore either played out or were abandoned when economic conditions changed. By 1850, the production had essentially ceased. When a modern blacksmith examines a historical wootz blade, the first thing they notice is the complete absence of forge welding lines. The blade is monolithic. It was drawn from a single ingot through repeated heating and hammering, but there are no internal boundaries where separate pieces were joined. This is obvious under microscopic examination. The carbide bands run continuously through the entire structure without the discontinuities that characterize pattern-welded construction. This monolithic structure contributes to the blade's toughness. There are no weak points where welded joints might separate under stress. The entire blade flexes as a unified structure, with the carbide networks distributing stress throughout the material. Modern Damascus pattern blades are almost universally pattern welded because it's the only practical way to create visible banding using contemporary steels. The resulting pattern looks superficially similar, but lacks the structural integration of genuine wootz. The visual similarity is there, the mechanical equivalence is not. Paufler's 2006 publication in the journal Nature fundamentally changed how materials scientists viewed historical metallurgy. The presence of carbon nanotubes in medieval steel samples meant that nanotechnology wasn't a modern invention, it was a rediscovery. The wootz metallurgists had empirically developed a process that created nanoscale structures through bulk thermochemical methods, something that modern materials science struggles to achieve economically, even with precise process control. The research team used high-resolution transmission electron microscopy, HRTEM, to image the nanostructures directly. They measured carbon nanotubes with diameters of 10 to 20 nanometers, small enough that thousands would fit across the width of a human hair. These nanotubes were oriented parallel to the carbide bands and aligned with specific crystallographic planes in the iron matrix. The cementite nanowires were even more impressive. Cylindrical carbide structures just 2 to 5 nanometers in diameter, running for several micrometers through the steel. These nanowires formed naturally during the slow cooling process, driven by the same thermodynamic factors that create the macroscopic pattern. The study answered a question metallurgists had been asking for 150 years. What makes Damascus steel mechanically superior to other historical steels? The answer was architecture at the nanoscale. The anvil surface where wootz blades were forged shows distinctive wear patterns that differ from anvils used for conventional blacksmithing. The high hardness of wootz steel created localized impact damage on the anvil face, small divots and depressions, where the carbide-rich blade material impacted the iron anvil during forging. These wear marks are denser in the areas where blade edges were worked, where the concentrated carbide content created the hardest impacts. A skilled smith had to adjust their hammering technique for wootz. Conventional steel could withstand heavy blows when red hot. Wootz required more controlled, lighter blows to avoid fracturing the carbide networks. The forging was a process of gradual shaping rather than aggressive material removal. This technical knowledge was embodied in the smith's muscle memory, the exact force, timing, and rhythm of hammer blows that would shape wootz without damaging it. You couldn't learn this from written instructions. You had to forge hundreds of blades under supervision, gradually internalizing the feedback between hammer impact and material response. When that generation of master smiths died without apprentices, the knowledge died with them. The grinding process to shape the blade edge was particularly challenging with wootz steel. The carbide bands meant that the abrasive encountered alternating regions of high and low hardness. A grinding stone that cut effectively through the ferrite-rich bands would barely scratch the carbide-rich regions. The smith had to maintain constant pressure and angle, letting the stone slowly work through both phases. This created the characteristic edge geometry of Damascus blades. A very acute angle, typically 15 to 20 degrees per side, much sharper than most European swords, which used 25 to 30 degree edge angles. The wootz material could support this acute geometry because the carbide networks prevented the thin edge from deforming under load. The grinding also refined the surface pattern. As the stone removed material, it exposed different levels of the internal structure, creating the flowing pattern visible along the blade's length. A master grinder could manipulate this pattern to some degree by varying the grinding angle, emphasizing certain bands while minimizing others. The final edge was stropped with leather and fine abrasive compounds to achieve the legendary sharpness attributed to Damascus blades in historical accounts. The variation in pattern between different wootz blades tells us about the production inconsistencies in the crucible process. Some ingots produced very fine, tightly spaced patterns. These came from slow, controlled cooling that allowed many small dendrites to form. Other ingots showed coarse, widely spaced patterns, faster cooling, or different trace element concentrations that promoted larger dendritic structures. The finest patterns were most highly valued because they indicated optimal processing conditions. They also tended to correlate with better mechanical properties. The fine-scale carbide distribution provided more uniform hardness and toughness throughout the blade. But even inferior wootz with coarse patterns was superior to most contemporary steels. The nanoscale architecture formed regardless of pattern coarseness because the carbon nanotubes and cementite nanowires developed through the same thermodynamic processes. This explains why historical sources describe such wide variation in Damascus blade quality. They were all genuine wootz, but the processing conditions varied enough to create measurable differences in performance. The bellows operation required careful regulation to maintain optimal crucible temperature. Too much air forced into the charcoal fire creates excessively high temperatures and rapid fuel consumption. Too little air and the combustion becomes incomplete, producing carbon monoxide and dropping the temperature below the steel's melting point. The bellows operator, often an apprentice assigned this critical but unglamorous task, had to maintain steady, rhythmic pumping for hours during the crucible heating phase. The physical endurance required was substantial. Your arms and shoulders would be burning after the first hour. By the third hour, you're operating on pure muscle memory. Archaeological evidence shows that some larger furnaces used multiple bellows stations positioned around the fire pit, allowing operators to work in rotation. This also created more uniform air distribution, reducing temperature gradients that could affect crucible heating. The air supply wasn't just fuel regulation. It was a primary process control parameter that determined whether the crucible reached the correct temperature profile for successful steel production. The role of vanadium as a carbide-forming element explains much of the mystery surrounding wootz production's geographic specificity. Vanadium forms extremely stable carbides that nucleate preferentially during steel solidification. These vanadium carbide particles act as templates where carbon atoms can organize into nanotube structures during the slow cooling process. Without vanadium, the carbon remains dissolved in the iron matrix or forms conventional cementite structures. No nanotubes, no nanowires. The optimal vanadium concentration appears to be 0.1 to 0.3% by weight. Below 0.1%, there aren't enough nucleation sites for extensive nanotube formation. Above 0.3%, the steel becomes too carbide-rich and loses ductility. This narrow concentration range explains why only specific ore deposits produced suitable material. The vanadium content had to be high enough to enable nanotube formation, but not so high that it dominated the carbide chemistry. Modern attempts to recreate wootz by intentionally adding vanadium to steel have had limited success. The vanadium must be incorporated naturally during the smelting process, not added as an alloying element afterward. The distribution and chemical state of vanadium atoms in the steel structure differs depending on how they were introduced. The quenching experiments conducted by 19th-century European metallurgists revealed how little they understood about wootz's unique properties. They tested rapid oil quenching, water quenching, and brine quenching, standard heat treatment protocols for conventional steel. Every test resulted in blade fracture. The wootz structure couldn't tolerate the thermal shock. The mismatch in thermal expansion between carbide and ferrite created internal stresses that exceeded the material's fracture toughness. After dozens of failed attempts, some researchers concluded that Damascus blades were never heat-treated. They achieved their hardness purely through composition and slow cooling. This was correct but incomplete. The blades were heat-treated, just not in the way European metallurgy understood heat treatment. The repeated forging cycles with intermediate air cooling constituted a sophisticated thermomechanical processing sequence. Each heating and hammering cycle refined the microstructure, elongating the carbide networks and eliminating internal voids. The final slow cooling from forging temperature was the crucial step that preserved the nanoscale architecture. This was heat treatment, but it was integrated into the forging process rather than performed as a separate operation. The fracture surface of a broken Damascus blade is distinctive under magnification. The break doesn't follow a single plane. It zigzags through the material, following the path of least resistance through the alternating carbide and ferrite bands. The fracture surface shows a mixture of cleavage facets, where the carbide bands fractured in a brittle manner, and dimpled regions where the ferrite matrix failed in a ductile mode. This mixed mode fracture is exactly what you want in a blade material. The carbide bands provide hardness and wear resistance, but would be catastrophically brittle alone. The ferrite matrix provides toughness and energy absorption, but would be too soft alone. The composite structure combines both properties. When a Damascus blade encounters a hard obstacle during cutting, bone, armor, another blade, the impact energy is distributed through the carbide network, preventing localized yielding. The ferrite matrix prevents crack propagation, stopping any fractures that initiate in the carbide bands from running through the entire structure. The material is damage-tolerant at multiple scales. The organization of Persian and Syrian smithing workshops reveals a sophisticated division of labor. The master smith who actually forged the blades didn't produce the wootz ingots. Those arrived as trade goods from India. The master didn't perform the rough grinding. That was assigned to specialized grinders who understood abrasive techniques. The master didn't conduct the final polishing and etching. Finishing specialists handled those steps. The master smith's role was blade forging and heat management. That's where the critical expertise resided. Everything else could be learned relatively quickly by apprentices, but the forging process required years of experience to internalize the subtle cues that indicated correct temperature and working technique. This specialization made sense economically. The master's time was too valuable to spend on tasks that didn't require their unique skills, but it also created knowledge fragmentation. When wootz ingot supplies disappeared, the master smiths lost their livelihood, even though they still possessed forging expertise. The knowledge couldn't adapt to different materials because it was so specifically calibrated to wootz's unique properties. The polishing process revealed the pattern incrementally as surface layers were removed. Initial forging left the blade surface covered in scale, oxidized iron that formed during high-temperature exposure to air. This had to be removed through aggressive grinding with coarse stones. The underlying metal appeared uniform and gray at this stage. As finer abrasives were applied and the surface became smoother, the pattern began emerging. First as subtle variations in reflectivity, then as distinct bands with different optical properties. The carbide-rich bands took a higher polish than the ferrite-rich bands, creating the characteristic watered silk appearance. The final polishing stages used progressively finer abrasives, powdered minerals suspended in oil, applied with leather. This created a mirror finish where the pattern was fully visible. The polisher had to work carefully to maintain uniform surface removal across both carbide and ferrite regions. Uneven polishing would distort the pattern. A master polisher could enhance the pattern through selective pressure application, but couldn't fundamentally change it. The pattern was encoded in the blade's internal structure. Archaeological excavations of crucible steel production sites in southern India have revealed industrial-scale operations dating to the 5th to 8th centuries. Some sites show evidence of hundreds of crucibles processed simultaneously in large furnace complexes. The slag heaps contain tons of material, indicating sustained production over decades or centuries. This wasn't artisan craft production. This was proto-industrial manufacturing serving an export market. The furnace construction shows sophisticated understanding of thermal management. Stone-lined pits with carefully designed air inlet channels to promote even heating. Crucible placement patterns that optimized heat distribution while allowing workers access for charging and removing vessels. The economic investment required to establish these facilities was substantial. The infrastructure, fuel supply chains, ore procurement, skilled labor. This was organized industrial activity supported by capital investment and regional trade networks. When that economic system collapsed, the physical infrastructure remained, but the knowledge and organizational capacity disappeared. Modern materials. Science laboratories studying Damascus steel face a fundamental problem. Destructive testing destroys the very artifacts we're trying to understand. To fully characterize a wootz blade's internal structure requires sectioning, polishing, and microscopic analysis, processes that destroy the blade as a functional object. Museums are understandably reluctant to allow researchers to cut up rare historical artifacts for scientific study. This means that most of our detailed analytical data comes from blade fragments, broken specimens, or modern attempts at recreation. We have very few complete, intact historical blades that have been subjected to comprehensive microstructural analysis. The 2006 Paufler study used small blade fragments obtained from museums and collectors willing to sacrifice pieces for scientific research. The samples were tiny, a few millimeters across, but sufficient for transmission electron microscopy. This sampling limitation means our understanding of wootz steel is still incomplete. We have detailed data from limited specimens and must extrapolate to general conclusions about the material category as a whole. Museum collections contain dozens of blades labeled as Damascus steel that are almost certainly pattern-welded forgeries or misidentifications. The visual pattern can be faked. A skilled modern smith can create pattern-welded steel that looks convincingly like wootz to untrained observers. Without destructive testing or very sophisticated non-destructive analysis, distinguishing genuine wootz from clever imitations is difficult. Some Damascus blades in historical collections are actually European pattern-welded swords from the medieval or Renaissance periods, misattributed based on surface appearance. Others are 19th century attempts to recreate Damascus steel through various experimental techniques. Authentication requires a combination of provenance research, stylistic analysis, and, when possible, technical examination. X-ray fluorescence can identify elemental composition non-destructively. Magnetic properties differ between genuine wootz and pattern-welded constructions. Ultrasonic testing can sometimes detect internal structure without damaging the blade. But none of these methods are perfect, and the most conclusive test, microscopic examination of polished cross-sections, requires sacrificing the artifact. The final inspection of a completed wootz blade was both functional and aesthetic. The smith examined the pattern to verify that it extended consistently along the blade's length. Uneven pattern distribution indicated problems during forging. Perhaps the temperature wasn't uniform, or the hammering wasn't consistent. Such blades might be structurally sound, but would command lower prices. Flexibility was tested by bending the blade and verifying that it returned to straight. Excessive permanent deformation indicated insufficient carbon content or damaged carbide structure. Brittleness, fracture during flex testing, indicated excessive carbide formation or improper forging temperature. Edge sharpness was verified by cutting tests. Hair, cloth, or soft wood. The edge had to take and hold sharpness without microchipping or rolling. If the blade passed all inspections, it was ready for mounting and sale. If it failed, it might be reworked if the defects were correctable, or scrapped if the fundamental structure was compromised. The master smith's reputation depended on consistently producing blades that met quality standards. A single exceptional blade didn't establish reputation. Consistent excellence across hundreds of blades did. The knowledge extinction wasn't sudden. It was gradual erosion over several generations. The last documented wootz producers in India were active in the 1830s to 1840s. By 1850, production had essentially ceased. By 1870, no living smith possessed the complete knowledge to produce wootz from raw materials. Some fragments of knowledge survived. Bladesmiths in Damascus continued forging blades from existing wootz ingot stocks through the late 19th century. These smiths understood the forging process, but not the crucible steelmaking that produced the raw material. Metallurgists in Europe and America possessed chemical and thermal data about wootz composition, but not the procedural knowledge to recreate the production process. They could analyze, but not synthesize. By 1900, Damascus steel had transitioned from a living craft tradition to a historical curiosity, a lost technology that became the subject of romantic speculation and increasingly inaccurate mythology. The trace element hypothesis explains the production cessation better than any alternative theory. The specific ore deposits in southern India that contained optimal vanadium concentrations were geographically limited. As these mines were exhausted or became economically unviable, the supply of suitable ore dried up. Metallurgists trying to recreate wootz using different ore sources couldn't match the properties of historical steel because the trace element profiles were wrong. They might have similar carbon and iron content, but lacked the specific vanadium, molybdenum, and manganese ratios that enabled carbon nanotube formation. This wasn't something that could be easily fixed through metallurgical knowledge. Without modern analytical chemistry, the Smiths couldn't identify what was missing. They just knew that new ore sources didn't produce the same results as traditional ones. When the traditional ore ran out, the process failed, and nobody understood why. Modern attempts to recreate Damascus steel fall into two categories: authentic replication and aesthetic imitation. Authentic replication attempts to recreate both the visual pattern and the nanoscale microstructure through crucible processing of high-carbon steel with added trace elements. Some researchers have achieved partial success, producing steel with carbon nanotubes and similar mechanical properties to historical wootz. Aesthetic imitation produces the visual pattern through pattern welding or acid etching, but makes no claim to structural equivalence. These blades look like Damascus steel, but don't possess the same material properties. The distinction matters for understanding the historical achievement. Recreating the appearance is relatively straightforward. Modern smiths have been doing it successfully for decades. Recreating the nanoscale architecture requires precise control of composition and thermal processing that even modern metallurgy struggles to achieve consistently. The wootz smiths developed an empirical process that created nanotechnology through bulk processing methods. That remains an impressive achievement, regardless of whether they understood the nanoscale mechanisms. The carbon nanotube discovery forced revision of materials science history. Before 2006, the narrative was that nanotechnology emerged in the late 20th century through advances in microscopy and material synthesis. Carbon nanotubes were discovered by Sumio Iijima in 1991 using electron microscopy to examine carbon soot. The Damascus steel findings showed that carbon nanotubes had existed in human-made materials for at least 1,500 years before their formal scientific discovery. Medieval craftsmen created them accidentally through empirical process development. This revelation highlighted an important point about technological knowledge. Understanding mechanism isn't necessary for effective practice. The wootz metallurgists didn't need to know about carbon nanotubes to create them. They needed to know which ores to use, how to build crucibles, and how to control furnace temperature. Empirical knowledge can sometimes achieve results that theoretical understanding struggles to replicate. The Damascus blade mythology that developed in the 19th to 20th centuries often obscured the actual historical reality. Stories circulated about blades that could cut through rifle barrels, slice falling silk scarves, or remain sharp indefinitely without maintenance. Some of these accounts contain kernels of truth. Wootz steel did have exceptional properties, but the exaggerations transformed the material into something magical. The reality was impressive enough without embellishment. Damascus blades were superior to most contemporary swords in hardness, toughness, and edge retention. They commanded premium prices for good reasons, but they weren't indestructible, didn't violate physical laws, and could be damaged or broken under sufficient stress. Separating the factual history from romantic mythology requires careful examination of period sources, metallurgical analysis of surviving blades, and skepticism about spectacular claims that lack corroborating evidence. The actual achievement, creating nanoscale structures through empirical metallurgy, is remarkable enough. The current state of Damascus steel knowledge represents an unusual situation in materials science. We have historical artifacts we cannot fully reproduce using modern technology and scientific understanding. This reverses the normal trajectory, where contemporary materials engineering surpasses historical capabilities. Research continues. Material scientists are experimenting with different trace element additions, modified thermal processing cycles, and alternative production methods, trying to recreate the full suite of wootz properties. Some recent work has achieved promising results, but we still don't have a production process that reliably generates the nanoscale architecture observed in historical wootz steel. The empirical knowledge that medieval craftsmen developed through generations of practice hasn't been fully captured by contemporary scientific methodology. This represents both a challenge and an opportunity for materials research. Understanding how pre-industrial metallurgists achieved results that modern science finds difficult to replicate might reveal insights applicable to contemporary nanotechnology development. When you hold a genuine Damascus blade forged 500 years ago, you're holding a nanomaterial created before anyone knew atoms existed. The steel in your hand contains carbon structures measuring 10 nanometers across, organized into networks that extend through the entire blade. The pattern you see on the surface is the macroscopic manifestation of processes occurring at the atomic scale. Carbon atoms, organizing into tubes and wires, guided by vanadium catalysts and shaped by thermal gradients inside a ceramic crucible. The knowledge that created this material is lost. The ore sources are exhausted. The craftsmen are dead, but the blades remain. Physical evidence of technological sophistication that challenges our assumptions about what was possible with pre-industrial metallurgy.